Look up at the night sky on a clear night, far from any city, and count what you can see. With the naked eye, on the very best night of your life, you might count 5,000 stars. That sounds like a lot. It is, in fact, almost nothing. Our galaxy alone contains between 200 billion and 400 billion stars, a number so large that if you counted one per second without stopping, it would take you between 6,000 and 13,000 years to finish, longer than the entire span of recorded human civilization, from the first Sumerian clay tablets to this moment. And our galaxy is one of at least 2 trillion galaxies in the observable universe. 2 trillion. And here is the thing that almost nobody pauses on, the thing that should stop you cold. The observable universe is not the universe. It is just the part we can see. And the part we cannot see may be so much larger than what we can, so incomprehensibly, so staggeringly, so structurally larger, that the 2 trillion galaxies we can observe may represent a fraction of the whole, so small it would be embarrassing to call it a fraction. It might be closer to rounding error. If you enjoy videos that take the largest questions in cosmology and work through them with precision and care, but refuse to let scale become mere spectacle, but instead make it mean something, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about this topic is also the most understandable one. Most people, when they hear the phrase the universe, assume it refers to everything that exists, the totality of space, time, matter, and energy. They assume that when astronomers say the universe is 93 billion light years across, they are describing the full extent of existence. They assume that the cosmic horizon, the boundary of what we can observe, is approximately the boundary of what there is. This assumption is wrong, not approximately wrong, precisely, categorically, fundamentally wrong. The cosmic horizon is not the edge of the universe. It is the edge of our visibility. It is the distance beyond which light has not had enough time, in the 13.8 billion years since the Big Bang, to reach us. Behind that horizon, in every direction, space continues, and the current best evidence from cosmology, from the mathematics of inflation, and from the measured geometry of the observable universe, suggests that it continues for an almost inconceivable distance. The boundary of what we can see is a boundary drawn by the speed of light and the age of the universe. It is not a wall. There is no wall. The universe did not end at the edge of your flashlight beam just because your flashlight beam ended there. To understand why this is, and to understand what the evidence actually tells us about the true size of the universe beyond our horizon, you need to understand 3 things: what the observable universe actually is, and why it has the size it does; what happened in the first fraction of a second after the Big Bang, in the period called inflation, and what the geometry of space tells us about the extent of what lies beyond the horizon. Each of these is a separate argument. Each of them, independently, points in the same direction, toward a universe vastly, perhaps infinitely, larger than what we can see. Together, they make a case that is not merely speculative, it is grounded in the best tested physics we have. And it leads to conclusions that should change how you think about your place in the cosmos. Begin with the observable universe itself and what it means to have a cosmic horizon. The universe began, as best we can determine from the physics of general relativity, particle physics, and observational cosmology, approximately 13.8 billion years ago, in a state of extraordinary density and temperature. In the earliest moments, the universe was so hot and dense, but atoms could not exist. The entire cosmos was a plasma of quarks and gluons, then of protons and neutrons, an electron opaque to light and death, paling, filled with a radiation field so intense that photons could not travel more than a tiny distance before interacting with the surrounding matter. This plasma expanded, it cooled. After approximately 380,000 years, the temperature dropped to around 3,000 Kelvin, hot, but cool enough for electrons and protons to combine into neutral hydrogen atoms for the first time. The universe became transparent. The photons that had been trapped in the plasma were suddenly free to travel, and they have been travelling ever since, cooling as the universe expanded. And today, they form the cosmic microwave background, a faint afterglow of radiation that fills the entire sky, arriving from every direction at a temperature of 2.725 Kelvin, the coldest large-scale temperature in the known universe. You have probably heard of this. You may not have considered what it tells us about the structure of the horizon. Here is what it tells us. The cosmic microwave background radiation, the CMB, was emitted from a surface that was, at the time of emission, roughly 42 million light-years away from us. At that moment, 380,000 years after the Big Bang. The universe has expanded enormously since then. The matter that emitted the CMB photons that are arriving at Earth today is now, in the current epoch, approximately 46 billion light-years away. That is the radius of the observable universe, 46 billion light-years in every direction, a sphere of roughly 880 cubic billion light-years of space, centered on Earth. Not because Earth is special, because the horizon is defined by the speed of light and the time elapsed since the Big Bang, and it is therefore centered on any observer everywhere. So, what is the radius thinking, or where word is not the same way? An astronomer in a galaxy 10 billion light-years from us has their own observable universe, also 46 billion light-years in radius, also centered on them. Our observable spheres overlap enormously, but they are not identical. There are regions within their observable universe that are not within ours, and vice versa. The observable universe is not a fixed object. It is a perspective. It is what any given observer can see from where they are in space and time. But before we go further, we need to understand how we know the universe is expanding at all, because the discovery of the expansion is one of the most important events in the history of science, and it is the foundation on which everything else rests. It was not always known. For most of human history, the universe was assumed to be static, eternal, and essentially the same at all times. Even Einstein, when he first applied his general relativity equations to the universe as a whole in 1917, found that his equations naturally predicted a dynamic universe, one that was either expanding or contracting. He found this deeply uncomfortable. A dynamic universe implied a beginning, and a beginning implied the unsettling question of what came before. He introduced a term into his equations, the cosmological constant, a kind of built-in repulsive pressure that he tuned to exactly balance gravity and hold the universe static. He called it, later, his greatest blunder. We will return to the cosmological constant, because it did not stay blundered for long. In 1923, Edwin Hubble, working at the Mount Wilson Observatory in California, with the most powerful telescope then in existence, a 100-inch reflector, sitting on a mountaintop in the San Gabriel Mountains, a telescope so large that its mirror alone weighed 5 tons, resolved individual stars in the Andromeda Nebula. This was already controversial, Many astronomers believed the Andromeda Nebula was a cloud of gas within our own Milky Way. Hubble's resolution of individual stars changed the picture immediately. Among the stars he resolved were a specific type called Cepheid variables, stars that pulsate in brightness with a period precisely related to their absolute luminosity. Brighter Cepheids pulsate more slowly. By measuring the period of a Cepheid's pulsation, you can calculate how intrinsically bright it is. By comparing that intrinsic brightness to how bright it appears in the sky, you can calculate how far away it is. The way you can estimate how far away a streetlight is from how bright it looks, if you know what wattage bulb it has. Hubble measured the Cepheids in Andromeda. He calculated the distance, approximately 900,000 light-years, a figure that placed it decisively outside the Milky Way, whose diameter was known to be around 100,000 light-years. The Andromeda Nebula was not a nebula at all. It was a galaxy, an entire separate Milky Way, a system of hundreds of billions of stars existing at a distance 9 times the diameter of our own galaxy. The Milky Way was not the universe. It was one city in a cosmos of cities. The universe was suddenly hundreds of thousands of times larger than anyone had thought. This was, in its own right, one of the greatest expansions of the known in human history. The discovery that the objects astronomers had catalogued as spiral nebulae were in fact separate galaxies, each containing billions of stars, each separated from the Milky Way by unimaginable distances. But this was only the beginning of what Hubble would find. In 1929, Hubble published a paper that established what we now call Hubble's law, the observation that nearly all galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. He arrived at this by measuring the redshift of galaxy spectra, the shift of spectral lines toward longer, redder wavelengths caused by the Doppler effect of recession, in the same way that the pitch of a receding train's horn drops as the train moves away from you. The redshift of a galaxy encodes its recession velocity. By plotting recession velocity against distance for a sample of galaxies, Hubble found a linear relationship. Double the distance, double the recession speed. The universe is expanding. Every galaxy is moving away from every other galaxy, not because galaxies are moving through space, but because space itself is stretching, growing, and the galaxies are carried along with it, like raisins in an expanding bread dough. This observation killed the static universe. Einstein removed a cosmological constant from his equations. The universe had a beginning. It was smaller in the past, denser and hotter, and the extrapolation backward in time eventually led to the singular state of extreme density and temperature that Hubble's Belgian contemporary, the priest and physicist Georges Lemaitre, had proposed as the primeval atom, what we now call the Big Bang. The universe was not eternal. It was born. And because it was born at a specific moment, and because light travels at a finite speed, it follows with mathematical inevitability that there is a horizon, a distance beyond which we cannot see, because the light from there has not had time to arrive. The observable universe is bounded not by a wall in space, but by a wall in time, the time elapsed since the Big Bang, combined with the finite speed of light. And then, in 1998, came the second great shock in the history of our understanding of the universe's expansion. 2 teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at various epochs in its history. Type Ia supernovae are stellar explosions with a characteristic peak luminosity. Like Cepheid variables, they are intrinsically bright in a way that can be calculated, so their apparent brightness tells you how far away they are. By measuring the distances to Type Ia supernovae at various redshifts, various epochs in the past, you can reconstruct how the universe's expansion rate has changed over time. The expectation going into the project was that the expansion should be slowing down. Gravity pulls matter together, and matter fills the universe, so gravity should be acting as a brake on the expansion, decelerating it. The question was just how much. The answer was not some. The answer was it is not decelerating at all. It is accelerating. Distant supernovae were fainter than expected, which meant they were farther away than expected, which meant the expansion was faster than expected, which meant the expansion had sped up rather than slowed down. The universe's expansion is accelerating. Something is pushing it apart, overcoming the gravitational attraction of all the matter in the universe and causing space to expand faster and faster as time goes on. Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. The agent of the acceleration is called dark energy, not because we understand it, we do not, but because it does not emit light, and it drives expansion. Its simplest mathematical description is Einstein's cosmological constant, the same term he introduced and then discarded, the energy density of empty space. In this description, every cubic meter of empty space contains a fixed amount of energy, an extremely small amount, roughly corresponding to the rest mass energy of a few protons per cubic meter of space. And this energy causes space to expand. The cosmological constant fits the data. And cosmological constant fits the data. Every precision measurement of the expansion history of the universe, from Type Ia supernovae, from the CMB, from baryon acoustic oscillations, from large-scale structure surveys, is consistent with a cosmological constant. Dark energy accounts for approximately 68% of the total energy content of the universe. Ordinary matter, everything you can see, everything made of atoms, everything ever detected by any instrument, accounts for about 5%. Dark matter, the gravitationally interacting but electromagnetically invisible substance, whose presence is inferred from galaxy rotation curves and gravitational lensing, accounts for about 27%. That is the fraction of the universe that humanity has directly detected and studied. 95% is dark. The accelerating expansion has a direct and profound implication for the size of the universe that is accessible to us. Because the expansion is accelerating, because galaxies beyond the Hubble radius are receding faster than light, and this recession rate is growing, the observable universe is not growing with time. It is in fact slowly shrinking in terms of the number of galaxies it contains. Distant galaxies are accelerating away from us. Some galaxies that are currently within our past light cone, galaxies whose light we can now receive, will eventually pass beyond the point where their current light can ever reach us. As the accelerating expansion continues, more and more of the universe enters a permanently inaccessible region. Our cosmic island is gradually being isolated. In the far future, in tens of billions of years, the only galaxies visible to the inhabitants of the Milky Way will be those in our immediate local group, the few dozen galaxies gravitationally bound to us. Everything else will have receded beyond the horizon, red-shifted into invisibility, gone. The sky will still contain stars, billions of stars, in our own and neighbouring galaxies, but the vast cosmic web of distant galaxies that current telescopes reveal will be inaccessible. The evidence for the universe's past, for the expansion, for the hot Big Bang, will have been swept beyond the observable horizon. Future inhabitants of the far future universe, if they exist and look up, will have a cosmology problem we do not have. They will have very little evidence that there is anything beyond their local neighbourhood. They might conclude, if they knew no better, that the universe is just a small cluster of gravitationally bound galaxies. They would be as wrong as Kepler was about the Milky Way, and they would have no way of knowing it. This is a reminder that the knowledge we have, the evidence we have gathered, the cosmic web of distant galaxies that we have mapped, the primordial radiation that we have measured, is available to us only because we happen to exist at a particular cosmic moment, early enough that the universe's expansion has not yet swept the evidence away. Lucky, temporarily privileged. The window of observational richness that we currently enjoy, in which the full range of cosmic history from the C and B to the local group is visible in a single sky, will close. Not soon in human terms, in tens of billions of years. But it will close, and we are in it now, and we have the instruments to use it. This is not a reason for complacency, it is a reason for urgency. Now, the horizon itself. Why does the observable universe end at 46 billion light years? Not because space ends there. Space does not end there. Space, as far as we know, as far as the evidence indicates, continues beyond that boundary, without interruption. The horizon exists because the universe has a finite age. Light from objects beyond the horizon has not had time to reach us. It is travelling toward us right now, from regions of the universe that we presently cannot see, and will not reach Earth for billions or trillions of years, if it ever does. Depending on how fast those regions are receding from us due to the expansion of the universe. This last point is important. The universe is not merely expanding, the expansion is accelerating. The most distant galaxies we can currently observe are receding from us faster than the speed of light. Not because they are moving through space at that speed, nothing moves through space faster than light, but because the space between us and them is expanding, and the expansion of enough space adds up. A galaxy 14 billion light years away recedes from us at roughly the speed of light. Beyond a certain distance, called the Hubble radius, currently about 14 billion light years, the recession velocity exceeds the speed of light, and light emitted from those regions will never reach us. Never. Not with more time. Not with better telescopes. The light from those regions is fighting against an expansion that grows faster than the light can travel toward us, and the light is losing. Forever. This means the observable universe is not just our current view, it is our permanent view. The Hubble radius defines the boundary beyond which no new information will ever reach us, no matter how long we wait. Objects currently beyond the Hubble radius, but within our past light cone, objects whose ancient light is arriving at us now, sent billions of years ago when those regions were closer, are visible to us now. But any light they emit today will never reach us. Our view of those regions is frozen in the past and growing no more recent. The observable universe is a sphere, not just bounded by where light has had time to travel, but also by where it will ever be able to travel. given the accelerating expansion. We are, in a deep sense, causally isolated from the vast majority of space, not just today, permanently. This isolation, this permanent causal disconnection from most of the universe, is itself one of the most profound facts in cosmology. It means that most of what exists is forever beyond our reach, forever beyond our knowledge, in the direct observational sense. We can know that those regions exist. We can calculate what they should be like based on the physics we know. But we cannot see them. We cannot receive a signal from them. We cannot, in principle, ever interact with them. The universe has a region that is observable to us and a region that is not, and the ratio between those two regions may be so extreme that calling the observable universe a sample of the whole would be like calling a single hydrogen atom a sample of the Earth's oceans. But how large is the unobservable universe? To answer this, we need to talk about inflation. In 1979, a physicist named Alan Guth was working on a problem in cosmology that had been nagging at theorists for years. It was called the horizon problem, and it was this: the cosmic microwave background radiation is extraordinarily uniform. Everywhere you look on the sky, in every direction, the temperature of the CMB is 2.725 Kelvin, varying by no more than about 1 part in 100,000. This uniformity is remarkable because regions of the CMB on opposite sides of the sky, separated by 180 degrees, are so far apart that given the speed of light and the age of the universe, they could never have been in causal contact. There had never been enough time for a signal to travel from one side to the other. They could not have communicated. They could not have reached thermal equilibrium with each other the ordinary way, by exchanging heat until they reached the same temperature, the way a hot cup of coffee eventually reaches room temperature in a cool room. They were causally disconnected in the standard Big Bang model from the very beginning, and yet they are at the same temperature, to 1 part in 100,000. Why? The standard Big Bang model, without inflation, has no answer. You simply have to accept the uniformity as an initial condition, as a brute fact about how the universe started, with no explanation for why it started that way. Physicists are deeply uncomfortable with brute facts. A brute fact is a sign that the model is missing something. But the horizon problem was not the only problem. There was also the flatness problem. The universe, as we have discussed, is very close to spatially flat. In the standard Big Bang model, this flatness requires extraordinary fine-tuning of the initial conditions. The universe's spatial flatness is described by a parameter called the density parameter, omega, the ratio of the universe's actual density to the critical density required for flat space. If omega equals exactly 1, the universe is perfectly flat. If omega is even slightly greater than 1, the universe is positively curved and will eventually recollapse. If omega is even slightly less than 1, the universe is negatively curved and will expand forever at an accelerating rate determined by the geometry. The problem is that in the standard Big Bang model, omega equals 1 is an unstable equilibrium. Any tiny deviation from exactly 1 in the early universe is amplified over time. For omega, 1 to 60.8 billion years of evolution, it would have had to be fine-tuned to within 1 part in 10 to the power of 6 of exactly 1 in the first second of the universe's existence, not approximately 1. And there was a third problem, the magnetic monopole problem. Grand unified theories, the class of theoretical frameworks that attempt to unify the electromagnetic force with the strong and weak nuclear forces, predicted that the hot early universe should have produced large numbers of magnetic monopoles and, having many powerful results, exotic particles with a single magnetic pole, rather than the dipole structure of ordinary magnets. Magnetic monopoles have never been observed. If they were produced in the quantities predicted by grand unified theories, they would be so numerous that they would dominate the energy density of the universe today, which they obviously do not. Where are all the magnetic monopoles? Gibbs inflation solved all three problems simultaneously. It solved the horizon problem by expanding a causally connected region to encompass the entire observable universe. It solved the flatness problem by stretching space so dramatically that any initial curvature is diluted to unmeasurably small values. Exponential expansion makes the universe flat, for the same reason that blowing up a balloon makes its surface flatter. And it solved the magnetic monopole problem by diluting any monopoles produced before inflation to such a low density that the expected number in the observable universe is less than 1, effectively 0. 3 deep problems in cosmology, solved by one mechanism in one paper. Goth recognized, even as he published, that his original model, which he called old inflation, had a technical problem. The exit from inflation, in his model, occurred through bubble nucleation. The inflaton field tunneled quantum mechanically from its high-energy false vacuum state to its lower-energy true vacuum state, forming bubbles of true vacuum that expanded and coalesced. The problem was that the bubbles could never successfully merge. The inflating space between them expanded too fast for the bubbles to percolate and reheat the universe uniformly. The model produced a universe full of disconnected domains, not the smooth, uniform universe we observe. This became known as the graceful exit problem. The resolution came in 1982, almost simultaneously from Endre Linde at the Lebedev Physical Institute in Moscow and from Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania. They proposed new inflation, in which the inflaton field does not tunnel abruptly, but rolls slowly down a gentle potential energy landscape, like a ball rolling slowly down a nearly flat hillside, remaining in a high energy state for a long time before reaching the minimum. This slow roll inflation ends gracefully and uniformly, without the bubble problem, and produces precisely the nearly scale-invariant spectrum of density fluctuations that the CMB observations later confirmed. The slow roll paradigm became the standard framework for inflation and remains the basis for the vast majority of inflationary models today. Linde later developed another version, chaotic inflation, in which the inflaton field starts in a random state with different initial values in different regions, and regions with high initial values undergo long periods of inflation, while regions with low initial values do not. This model naturally leads to eternal inflation, as different regions exit inflation at different times, producing the patchwork of bubble universes we discussed. Chaotic inflation is, in many respects, the most natural version. It requires no fine-tuning of initial conditions, because essentially any initial state of the inflaton field leads to at least some inflation, and sufficiently high initial values lead to the enormous inflation needed to explain the observable universe's uniformity and flatness. The evidence for inflation has been accumulating steadily since the 1990s. Combat. The COBE satellite, launched in 1989, first detected the CMB temperature fluctuations and found them to be consistent with the scale invariant spectrum predicted by inflation. WMA sharpened this to high precision. Planck sharpened it further, measuring the spectral index, the slight tilt away from perfect scale invariance that most inflationary models predict, with a precision that allowed cosmologists to rule out entire classes of models. The spectral index measured by Planck is NS equals 0.9649 plus 0.0001 0.042, meaning the spectrum is nearly, but not perfectly, scale invariant, tilted slightly toward more power on large scales, exactly as simple slow-roll inflation. The simplest inflationary models, those with a single slowly rolling scalar field and the most natural potential energy landscapes, are precisely consistent with the CMB data. There was a dramatic moment in 2014 when the BICEP-2 experiment, a telescope at the South Pole designed to measure the polarization of the CMB, announced the detection of a specific polarization pattern called B-mode polarization, a swirling cowboy bee, girl-like pattern in the CMB polarization maps that would be a signature of primordial gravitational waves produced during inflation. If confirmed, it would have been the first direct detection of the imprint of inflation on the CMB, a discovery of the highest significance. The announcement was global news. For a few months, the physics community celebrated. Then, the Planck satellite released polarization data showing that the galactic dust emission, a foreground contaminant, was substantially larger than BICEP-2 had assumed, and that the detected B modes were fully consistent with dust foreground rather than primordial gravitational waves. The detection was not confirmed. The celebration ended. The search continues. BICEP-Keck, the successor experiments, have continued to push to lower noise levels. The CMB-C4 experiment and the Simons Observatory, in development and early operations, will provide the next generation of sensitivity. The detection of primordial B modes remains one of the most sought-after discoveries in cosmology, not because B modes tell us nothing else, but because their amplitude directly encodes the energy scale of inflation. Detecting them would tell us how energetic the inflationary epoch was, and higher energy inflation is more likely to produce the eternal inflation scenario that implies a vastly larger universe. The amplitude of primordial gravitational waves from inflation is the knob that connects our laboratory, the observable universe, to the question of the universe's full extent. Guth's proposal was elegant and radical, in equal measure, in its original form, and its successors, new inflation, chaotic inflation, eternal inflation, have become the standard framework through which cosmologists think about the universe's origin, structure, and ultimate extent. But it is worth noting that inflation is not without its critics. Paul Steinhardt, one of the original architects of new inflation, has in recent decades become one of its most prominent critics, arguing that inflation is not predictive, that the space of inflationary models is large enough to accommodate almost any observational result, so that CMB measurements cannot truly confirm or refute inflation as a class of theories. Roger Penrose has proposed an alternative, cyclic cosmology, called conformal cyclic cosmology, in which the universe undergoes an infinite sequence of aeons, or epochs of expansion and eventual decay, with each aeon's Big Bang being the conformal boundary of the previous aeon's far future. The multiverse does not appear in Penrose's picture. The universe is, in a sense, its own predecessor. These alternatives are serious, debated, and not yet resolved. The question of what happened before or during the Big Bang, whether inflation is the right story, or whether some other mechanism explains the observed uniformity and flatness, is genuinely open. But among available alternatives, inflation remains by far the best supported by current evidence, and its implication of a vastly larger universe is its most dramatic and unavoidable consequence. Guth's proposal was elegant and radical in equal measure. Suppose he suggested that in the earliest moments of the universe, in the first tiny fraction of a second, perhaps between 10⁻³ and 10⁻³ seconds after the Big Bang, a span of time so brief that it defies human intuition entirely, the universe underwent a period of exponential expansion, not the slow, gradual expansion that has continued for the past 13.8 billion years. An explosive, exponential expansion in which the size of the universe doubled again and again and again, perhaps 100 times or more, in a fraction of a second. This period is called cosmic inflation, and it solves the horizon problem immediately. If the universe was, before inflation, an extremely small region, small enough for all parts of it to have been in causal contact, to have reached thermal equilibrium, and then inflation expanded it to an enormous size in a tiny fraction of a second, then the uniformity of the CMB is explained. The entire observatory universe, with all its uniformity, descended from a single tiny region that had plenty of time to reach a uniform temperature before inflation expanded it to cosmic scales. The uniformity is not a brute fact. It is a remnant of the pre-inflationary causal contact. Let us be precise about the timescales, because the numbers are genuinely extraordinary. The period of inflation, in most models, lasted from about 10 to 336 seconds to about 10 to 332 seconds after the Big Bang. The total duration is approximately 10,300,000 seconds, 100 million millionths of a second. In this time, this almost unconceivably brief interval, the region of space that would eventually become the observable universe expanded by a factor of at least 10 squared, and possibly by many orders of magnitude more. 10 followed by 26 zeros. To give this a calibrating reference, 1 meter multiplied by 10 squared is about 10 billion light years. The region of space that became the observable universe was, before inflation, roughly the size of a proton, 1/10 trillionth the size of the period at the end of this sentence. After inflation, it was roughly the size of a grapefruit. Not the current observable universe, which is 93 billion light years across, but the seed of it, the pre-recombination fireball that would eventually expand into what we see today. Inflation took something proton-sized and turned it into something grapefruit-sized, and then the standard Big Bang expansion took that grapefruit and expanded it for 13.8 billion years into everything we observe. Now, here is the crucial implication for the size of the universe beyond our horizon. And to mind, inflation did not stop at the edge of the observable universe. The observable universe is not special. Inflation acted on the entire pre-inflationary region of space, whatever its size was. And the pre-inflationary region of space that became the observable universe was one tiny patch of a much larger space. The rest of that larger space also inflated. It inflated by the same factor, or more, and it is not within our observable universe. It is beyond our horizon. And if inflation took a region and expanded it by a factor of at least 10 squared, the total inflated region is enormously, incomprehensibly larger than the part of it that is observable to us. How much larger depends on the duration and rate of inflation, which are parameters of the specific inflationary model and are not yet precisely known. But in the simplest, most conservative inflationary models, the total inflated region is at least 10 squared times larger in linear dimension than the observable universe, meaning the volume of the total inflated region is at least 10 to the power of 6/90th times the volume of the observable universe. 1 followed by 69 zeros. 69 orders of magnitude. For reference, the number of atoms in the observable universe is estimated at around 10,860,000,000. The volume ratio between the total inflated universe and the observable universe in conservative inflationary models is 10,649,000,000. That is 11 orders of magnitude less than the number of atoms in what we can see. The unobservable universe is not just larger, it is larger by amounts that make our entire observable universe vanishingly negligibly, almost insultingly small. But inflation does more than make the universe large. It makes predictions, and those predictions have been tested. This is not speculative cosmology in the pejorative sense, not imagination untethered from evidence. Inflationary models predict specific properties of the cosmic microwave background radiation, specifically the pattern of tiny temperature fluctuations, those 1 part in 100,000 variations we mentioned earlier, that were laid down by quantum fluctuations during the inflationary epoch and were then stretched to cosmic scales by inflation. The WMAP satellite, which operated from 2001 to 2010, measured these CMB fluctuations with extraordinary precision. The Planck satellite, which operated from 2009 to 2013, measured them with even greater precision. Both found that the pattern of CMB fluctuations is consistent with the predictions of simple inflationary models, including the spectrum of the fluctuations, how their amplitude varies with scale, and their statistical properties. The fluctuations are Gaussian, nearly scale invariant, and adiabatic, exactly what inflation predicts. Not approximately, not coincidentally, with a precision that has allowed cosmologists to rule out large classes of alternative models. Inflation also predicts that the universe should be spatially flat, or very close to it. Spatial flatness here means something specific. It means that the geometry of space is Euclidean, but parallel lines remain parallel, that the angles of a triangle add up to exactly 180 degrees, that the universe is not curved, like a sphere, or saddle-shaped, like a hyperbolic surface. The reason inflation predicts flatness is geometric. Whatever the curvature of the pre-inflationary space was, inflation stretches space so dramatically that any curvature is diluted away. Just as the surface of a balloon becomes less curved as you inflate it. Blow up a balloon to the size of the Earth, and any small patch of its surface will appear perfectly flat. Inflation does this to the curvature of space. Measurements of the CMB by WMA and Planck find that the universe is flat, or very nearly so, to a precision of better than 1%. The deviation from flatness, if any, is smaller than the current measurement uncertainty. The universe is flat. This flatness measurement is, quietly, one of the most profound observational results in the history of cosmology. Not because it confirms inflation, though it does, but because of what it implies about the size of the universe. A universe that is measurably curved, positively curved, like a sphere, so that parallel lines eventually converge, could be finite. A spherical universe wraps around on itself. If you travel in a straight line in a positively curved universe for long enough, you come back to where you started, the way a traveller going east on Earth will eventually return to their starting point. The size of such universe is set by the radius of curvature, how sharply curved it is. The more curved, the smaller. If the CMB measurements showed a significant positive curvature, we could infer a finite universe and calculate roughly how large it was. They do not show this. The universe is flat, or so close to flat that the deviation is undetectable. And a flat universe, or an infinitely flat one, is in principle infinite. Not just large, infinite. Infinite in spatial extent, containing infinite matter, infinite galaxies, infinite copies of every possible configuration of atoms, including, almost certainly, exact or near exact copies of you, your planet, your civilization, at some incomprehensible but finite distance from here. This is the claim that makes people uncomfortable, so let us approach it carefully. If the universe is spatially infinite, if space extends without limit in all directions, then by the mathematics of probability, any configuration of matter that is possible and has a non-Rosa probability of occurring will occur, not just once, but infinitely many times, scattered through the infinite volume of space. This is not mysticism, it is combinatorics. There are only a finite number of ways to arrange a finite number of particles in a finite volume. If you have infinite volume and finite local arrangements, those arrangements must repeat. The physicist Max Tegmark calculated that the nearest exact duplicate of our observable universe, a sphere 93 billion light-years across, in which every particle is in exactly the same position and state as in our own observable universe, would be approximately 10 to the power of 10 near 115 meters away. That number is so large that it has no meaningful name. It is not a distance you can contemplate directly, but it is a finite distance. And in an infinite universe, finite distances are always eventually reached. Let us pause on this, because the temptation is to dismiss it as philosophy rather than physics. But consider the structure of the argument. The universe is spatially flat to within measurement precision. A spatially flat universe has zero curvature. Zero curvature, if taken literally and not as a approximation to some small but non-essential curvature, implies infinite spatial extent. The observable evidence, the CMB flatness measurement, is consistent with an infinite universe. It does not prove it, because the measurement has error bars, and a slightly non-flat universe would also look flat within measurement precision. But it is consistent with it, and if the universe is infinite, then the existence of distant duplicates is not a speculation. It is a mathematical consequence of the laws of probability applied to infinite space. This is one of the places where cosmology and philosophy intersect, unavoidably. Philosophers of science have long argued about what counts as a scientific prediction, whether statements about regions of the universe that can in principle never be observed are scientific at all, or whether they belong to the realm of metaphysics. Some cosmologists, following this line, argue that the size of the unobservable universe is not a scientific question in the standard sense, because it cannot be tested by observation. Others argue, with equal force, that if a theory, inflation in this case, is tested and confirmed in the observable realm, its predictions for the unobservable realm deserve the same credence as any other prediction of the theory. You do not get to accept the parts of a physical theory that are confirmed by observation and reject the parts that are not, without a principled reason for the rejection. If inflation works, and it works extraordinarily well, then its implication of a vastly larger universe deserves to be taken seriously, not as certain truth, but as the best supported available hypothesis. But there is a deeper version of this argument, one that goes beyond inflation entirely, and it comes from a different direction, from the mathematics of the inflationary process itself, and from what happens when inflation ends. Inflation is driven by a quantum field, called the inflaton field, that exists in a high energy state, releasing energy as it rolls toward a lower energy state, and that energy drives the exponential expansion. In the simple picture of inflation, the inflaton field rolls smoothly toward its minimum energy state, and inflation ends everywhere simultaneously, after which the energy of the inflaton is converted to the particles and radiation of the hot Big Bang. This is the picture I have been describing, and it is the picture that reproduces the uniformity of the CMB and the flatness of the universe. But the inflaton field is quantum mechanical, and quantum fields fluctuate. At any given point in space, the quantum fluctuations of the inflaton field can cause it to jump upward in energy, away from the minimum, not toward it, at random. If this happens, inflation continues in that region instead of ending. The region inflates further. It grows. And in the meantime, the surrounding regions, where the inflaton field happened to roll toward its minimum, have exited inflation and become regions of normal hot Big Bang cosmology, regions like our own. So you get a patchwork, regions where inflation's ended, each becoming a separate hot Big Bang universe, surrounded by still inflating space. But the surrounding inflating space continues to grow exponentially. And in that exponentially growing space, more quantum fluctuations cause inflation to continue here, end there. More patches exit inflation. More hot Big Bang universes form. The inflating space is always producing more volume, faster than the regions that exit inflation can consume it. Inflation, once started, never completely stops. It continues, globally, forever. This is the picture known as eternal inflation. And if eternal inflation is correct, if the quantum fluctuations of the inflaton field inevitably cause inflation to continue indefinitely in some regions while ending in others, then the universe is not just larger than we can observe. It is an infinite, ever-expanding space, seeded with an infinite number of regions that have exited inflation and undergone their own Big Bang expansions. Each of these regions is, in effect, a separate universe, separated from all others by intervening space that is still inflating and that expands so rapidly that no signal, no matter how fast, could ever cross it. Each of these regions may have different physical properties, depending on the details of how the inflating field settled into its minimum energy state in that particular region. Different values of the cosmological constant, the energy of empty space that drives the accelerating expansion, different masses of fundamental particles, different strengths of the four forces, different physics. This is the multiverse, or more precisely, this is the inflationary multiverse, one of several distinct multiverse concepts in modern physics. The word carries a lot of baggage, some of it earned, some of it not. In popular culture, multiverse has become a synonym for anything goes, for a narrative device in which any story can be told, any outcome is possible, any contradiction is resolvable by appealing to a parallel world where things are different. The inflationary multiverse is not this. It is a specific, quantitative prediction of a specific physical mechanism, eternal inflation, which itself follows from the same quantum field theory framework that describes particle physics with extraordinary precision. Applied to the inflationary epoch of early universe cosmology, it is not science fiction. It is theoretical physics, and it is controversial, legitimately controversial, but for reasons of scientific methodology, not for reasons of implausibility. It is worth pausing here to lay out the full landscape of multiverse concepts, because they are often conflated. and the conflation causes confusion. The physicist Max Tegmark proposed a useful taxonomy, dividing multiverse concepts into 4 levels of increasing extremism, each based on different physical assumptions, and each having a different relationship to observational science. The level 1 multiverse is the simplest and most conservative. It is simply the region of space beyond our observable horizon, what we have been discussing. If the universe is infinite and spatially uniform, then regions beyond our horizon exist, contain matter, and are physically real in the same sense that distant galaxies we can currently observe are physically real. They are simply too far away for their light to have reached us. No exotic physics required, no new principles invoked. The level 1 multiverse is just the universe, if the universe is big enough. The level 2 multiverse is the eternal inflation picture, the patchwork of bubble universes, separated by still inflating space, each with potentially different values of the physical constants. This requires eternal inflation, which requires quantum fluctuations of the inflaton field, which requires quantum field theory applied to early universe cosmology. It is a larger theoretical step than level 1, but it is grounded in physics that is at least partially tested. The level 3 multiverse is the quantum many-worlds interpretation of quantum mechanics. When a quantum system is measured, the Copenhagen interpretation says the wave function collapses to a specific outcome. The many-worlds interpretation, proposed by Hugh Everett in 1957, and taken seriously by a significant fraction of physicists, says nothing collapses. Instead, the universe branches, with every possible outcome of every quantum measurement occurring in some branch. The branches are real, but do not interact. Each is effectively a separate universe, evolving alongside all the others, but unable to communicate with them. In this picture, every quantum event that could go differently does go differently in some branch. The number of branches is incomprehensibly large, vastly larger than the level 1 or level 2 multiverse, and grows constantly with every quantum event in the universe. Many worlds requires no new physics. It is a straightforward, if radical, interpretation of the quantum mechanical formalism. Its multiverse is a logical consequence of taking the equations of quantum mechanics literally, without adding any additional collapse postulate. The level 4 multiverse is the most extreme, the mathematical multiverse, in which every logically consistent mathematical structure corresponds to a physically real universe. Not just universes with different physical constants, or universes where quantum mechanics branched differently, but universes with entirely different laws of physics, different mathematics, different logical structures, different forms of existence. This is the territory of pure philosophy, perhaps, though Tegmark argues it follows from the observation that our universe seems to be describable by mathematics, and asks why that particular mathematical structure should be privileged above all others. It is a profound question, but it is not at present connected to any observational program. These 4 levels are conceptually distinct and have different degrees of grounding in established physics. The level 1 multiverse, the region beyond our horizon in a large or infinite universe, is the subject of this video, and it is the most firmly grounded. It requires only that the universe be large enough, which the evidence strongly suggests. Everything else is built on top of this foundation, each level adding additional theoretical scaffolding. There is, however, a current crisis in cosmology that bears directly on how well we think we understand the universe's expansion, and therefore on how confident we should be in our inferences about what lies beyond the horizon. It is called the Hubble tension, and it is genuine, persistent, and unresolved. The Hubble constant, the proportionality constant in Hubble's law, the number that tells you how fast the universe is expanding per unit distance, can be measured in two completely independent ways. The first is the early universe method. Using the cosmic microwave background, you fit the CMB power spectrum to the best cosmological model, and the fit gives you the Hubble constant as one of its parameters. The Planck satellite's 2018 measurement gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec, meaning that for every megaparsec of distance between galaxies, a megaparsec is about 3.26 million light-years. The expansion adds roughly 67.4 kilometers per second to their recession speed. The second method is the local universe measurement. You build a distance ladder, calibrating nearby distances using parallax measurements of nearby stars, then Cepheid variable stars and nearby galaxies, then Type Ia supernovae in more distant galaxies, building up a chain of distance measurements that lets you measure the recession speed of galaxies at various distances and thus the current expansion rate. The leading team doing this measurement, led by Adam Rees and collaborators, and using the Hubble Space Telescope and more recently the James Webb Space Telescope, consistently finds a Hubble constant of approximately 73 kilometers per second per megaparsec, about 8 to 9% higher than the Planck value. 8 or 9% sounds small. In the context of precision cosmology, it is enormous. The two measurements are made with independent methods, independent data, independent systematic effects. They should agree if the cosmological model, the standard lambda CDM model, with its specific mix of dark energy, dark matter, and ordinary matter, is correct. They do not agree. The discrepancy has been at roughly 4 to 5 sigma statistical significance for several years, not quite at the threshold of 6 sigma that particle physicists traditionally require to claim a discovery, but well above the 2 or 3 sigma level that might be dismissed as a fluctuation. Systematic errors in one or both measurements have been carefully investigated and do not explain the discrepancy. New data from the James Webb Space Telescope have confirmed the local measurement rather than resolving the tension. What does this mean? Nobody yet knows with certainty. There are several possibilities. One is that there is an unidentified systematic error in one of the measurements, some subtle bias in how distances are calibrated, some overlooked physical effect. This is possible, but it has proven resistant to resolution despite years of intense scrutiny. Another is that the standard cosmological model is wrong in some way that affects the early universe measurement, but not the local one. Perhaps dark energy is not a cosmological constant, but something that varies with time. Or perhaps there is an additional form of energy in the early universe that has not been accounted for. Theorists have proposed dozens of models to explain the tension, including early dark energy. Models in which a dark energy component was present in the early universe and slightly changed the expansion rate before recombination. No single model has been convincingly confirmed. The Hubble tension is important for this video, not because it changes the fundamental conclusion, the universe is much bigger than we can see, but because it is a reminder that our understanding of the universe's expansion history is not yet complete. The model we use to infer the geometry and size of the universe beyond our horizon is the standard lambda CDM model, and that model may have a flaw that the Hubble tension is pointing at. If the model is wrong in some way, our inference about the universe's size and geometry may be correspondingly wrong. Not wildly wrong, the evidence for a large flat universe is robust across many different measurements, but possibly wrong in ways that shift the numbers. Science is a process of successive approximation, and the Hubble tension is a sign that the approximation is not yet finished. The controversy is this: the inflationary multiverse is, almost by construction, unobservable. The other regions, the other bubble universes that had exited inflation, are separated from us by eternally inflating space. No signal crosses eternally inflating space. No light, no gravitational wave, no particle. The other universes are not merely far away. They are causally disconnected, permanently and irreversibly. We cannot observe them. We cannot test their existence directly. The prediction that they exist follows from eternal inflation, and eternal inflation follows from the quantum fluctuations of the inflaton field, which is itself not directly observable, but is inferred from the properties of the CMB fluctuations. The chain of inference is long. Each link is physics, but the endpoint of the chain is beyond the reach of any possible observation. Some physicists, following this logic, argue that the multiverse is not a scientific prediction at all, that science requires observational testability, and a prediction that is in principle unobservable is not science. Others argue that dismissing eternal inflation because its consequences are unobservable is throwing out the baby with the bathwater, that the underlying physics of inflation is tested and confirmed, that eternal inflation is a generic feature of most inflationary models rather than a fine-tuned exception, and that the appropriate response is to accept the prediction while acknowledging the limits of what we can verify. Still others point to an approach that might in principle provide at least indirect evidence, bubble collision signatures. If the inflationary multiverse is real, and if we are a bubble universe that formed when inflation ended in our region, then occasionally other bubble universes form nearby in the inflating space, that is, and their expanding bubble walls can collide with ours. Such a collision would leave a specific signature in the cosmic microwave background, a circular disk of slightly different temperature, roughly uniform within the disk, at a specific location on the CMB sky. Several searches for such signatures have been conducted, using WMAP and Planck data. None have found a statistically significant signal. This is consistent with either the multiverse being false, or with bubble collisions being sufficiently rare in our particular history that we have not experienced a detectable one. The absence of a signal does not rule out the multiverse. It constrains the parameters of specific models. The search continues. But let us step back from the multiverse for a moment, because even without eternal inflation and its implications, even within the bounds of a single inflated region, a single universe, in the most conservative interpretation of the word, the evidence for a universe vastly larger than the observable portion is compelling and does not require any exotic physics. It requires only what inflation directly implies, that the inflationary epoch expanded space by a factor of at least 10 squared, that the observable universe is one small patch of the inflated region, and that the rest of the inflated region continues beyond our horizon. This is not the multiverse. This is just the universe. Big, much bigger than what we can see. Perhaps 10 squared times bigger in linear dimension, perhaps more. This is the part that is grounded in the most well-tested physics we have, and it alone should be enough to fundamentally shift how you think about the cosmos. Let's make this concrete. Think of the following analogy. You are standing at the edge of the ocean on a perfectly clear day. You can see to the horizon, roughly 5 kilometers, depending on your height above the surface. You know with certainty that the ocean extends beyond the horizon. You cannot see it, but you know it is there. The curvature of the earth is what limits your vision, not the extent of the ocean. Now imagine that you could measure the curvature of the ocean's surface with enormous precision and you found that the ocean was perfectly flat, or so close to flat that the deviation was less than your best measurement could detect. If the ocean were truly perfectly flat, geometrically, it would be infinite. There would be no horizon imposed by curvature. You would still have a visual horizon set by the limits of your eyesight, by the scattering of light in the atmosphere, but the ocean itself would go on forever. Your visual horizon and the edge of the ocean would be completely different things. This is exactly the situation in cosmology. The cosmic horizon, the boundary of the observable universe, is set by the speed of light and the age of the universe, our cosmological eyesight. The extent of space itself is set by the geometry of space, the curvature. We have measured the curvature. It is flat, or so close to flat that it might as well be. The observable universe is our visual horizon. The universe is the ocean. They are not the same thing. Now return to the numbers, because numbers are how physics speaks. The observable universe has a volume of roughly 4 by 10 cubed 32 cubic light years. It contains an estimated 2 by 10,012 galaxies, each with an average of perhaps 100 billion stars, giving somewhere around 10 squared 4 stars in the observable universe, a number larger than the estimated number of grains of sand on all the beaches of Earth by a factor of 10 million. In the observable universe alone, the scale is beyond comfortable intuition. Now consider that in the most conservative inflationary models, the total inflated universe is at least 10 squared times larger in linear dimension than the observable universe. The volume scaling goes as the cube of the linear dimension, so the volume of the total universe is at least 10 to the power of 6 to the power of 9 times the volume of the observable universe. The number of galaxies in the total universe, if the galaxy density is uniform, and on the very largest scales it should be, because inflation smoothed out any large-scale inhomogeneities, is at least 10 to the power of 6 to the power of 9 times 2 by 10 to the power of 12, or roughly 10 billion 163 galaxies. The number of stars is correspondingly 10 billion 953 stars. The number of atoms is around 10 billion 110 atoms. These are not numbers for which we have useful names or intuitions. They are numbers that exist only in mathematics and in the physical universe that mathematics describes. And these are the conservative estimates. In more aggressive inflationary models, or in models where inflation lasted longer, the numbers are larger, much larger. In eternal inflation models, the universe is infinite and the numbers become infinite, not larger than 10 to the power of 8(1). Infinite, formally, mathematically, actually infinite. Here is where the argument takes a turn that some find liberating and others find deeply unsettling. If the universe is infinite, or even if it is finite but vastly larger than the observable portion, then the question of what exists beyond our horizon is not merely academic. It has implications for how we understand our place in the cosmos. An infinite universe contains infinite matter. Infinite matter can arrange itself in infinite ways. Any finite region of infinite space, any bubble of 93 billion light-year radius, any observable universe contains a finite amount of matter in a finite number of possible configurations. In an infinite universe, those configurations must repeat. Not might repeat, must repeat by the mathematics of infinite sets. Somewhere, in the unobservable reaches of our own universe, Not in another bubble universe, not in some exotic parallel dimension, but in the same continuous space that contains the Milky Way. In the same physical universe, governed by the same laws, there is another you, an exact copy, or close enough to exact that the difference is a single misfolded protein in your left elbow. There are infinite copies. Some of them made different decisions at every fork in the road of their lives. Some of them are reading a different book right now. Some of them are watching a different video. Some of them are not watching anything, because something went differently at some point in the past, and they are not here to watch. This is the most disorienting implication of infinite space. Not black holes, not the Big Bang, not even the heat death of the universe, but this, that uniqueness, which we intuitively associate with identity, with selfhood, with meaning, is not a feature of an infinite universe. In an infinite universe, you are not unique. You are one of infinitely many. Your thoughts, your memories, your specific arrangement of atoms, all of it exists elsewhere, in infinite copies, with infinite variations. The universe, if infinite, is the ultimate plagiarist of itself. This does not mean your life is meaningless. Meaning is a category that operates at the scale of lives, of relationships, of choices and their consequences, a scale at which uniqueness within our observable universe is perfectly real and fully adequate. The nearest copy of you is unimaginably far away. You will never meet them. They cannot affect you, and you cannot affect them. They might as well not exist from any practical standpoint, but they do exist if the universe is infinite. And the question of whether the universe is infinite or merely much larger than what we can see is a genuine scientific question with genuine, partially testable implications. Let us talk about what, specifically, we might be able to learn about the universe beyond our horizon and what the limits of that knowledge are. Before doing so, it is worth establishing what we actually know about the large-scale structure of the observable universe, because that structure itself is remarkable, and it provides both the context for understanding what might lie beyond and the tools with which we probe the universe's geometry. The universe is not uniformly filled with matter. On the scale of individual stars and planetary systems, matter is mostly empty space with dense concentrations here and there. On the scale of galaxies, the concentrations become more organized. On still larger scales, tens of millions of light years and above, the distribution of galaxies reveals a breathtaking architecture, the cosmic web. Galaxies are not scattered uniformly through space. They are organized into a network of filaments, long, thin strands of galaxies and dark matter, stretching for hundreds of millions of light years, connected at their intersections by dense clusters of thousands of galaxies, the most massive gravitationally bound structures in the universe, separated by vast voids, regions of space largely empty of galaxies, spanning hundreds of millions of light years, where the density of matter is far below the cosmic average. The cosmic web is the largest structure in the universe, and it has been mapped in increasingly fine detail by successive galaxy surveys. The Sloan Digital Sky Survey, which mapped hundreds of millions of galaxies and quasars over a quarter of the sky. The Dark Energy Survey, which mapped hundreds of millions more in the southern hemisphere. And most recently, the Dark Energy Spectroscopic Instrument, or DESI, which is in the process of mapping tens of millions of galaxies in 3 dimensions with unprecedented precision. Within this cosmic web is imprinted a pattern of extraordinary scientific value: baryon acoustic oscillations, or BAO. In the early universe, before recombination, the plasma of protons and electrons was coupled to the photon radiation field. Any overdensity, any region slightly denser than average, would generate both a gravitational infall of matter and a pressure wave propagating outward through the plasma at the speed of sound in that plasma, roughly 170,000 kilometers per second, or about 57% of the speed of light. These sound waves propagated outward until recombination, when the plasma became neutral gas and the coupling between matter and radiation ended. At that moment, the waves froze. They travelled a fixed distance, approximately 490 million light years in today's units, accounting for the expansion since then, and then stopped. This distance is called the sound horizon, and it leaves a characteristic imprint in the distribution of galaxies. Galaxies are slightly more likely to be separated by approximately 490 million light years than by nearby distances. This preferred separation shows up as a bump in the statistical distribution of galaxy separations, and it has been measured with remarkable precision in large galaxy surveys. BAO is extraordinarily useful because the physical scale of the sound horizon can be calculated from first principles, from the known physics of the plasma, the radiation, and the geometry of the early universe, to high precision. By measuring the apparent angular size of the BAO feature at various redshifts, we measure the angular diameter distance to those redshifts, which encodes the history of the universe's expansion and geometry. BAO is in effect a standard ruler, a feature of known physical length at various distances, whose apparent angular size tells us the geometry of the space through which the light has travelled. Combined with the CMB, with type Ia supernovae, and with measurements of the growth rate of large-scale structure, BAO measurements form one of the four pillars of precision cosmology. And they consistently point in the same direction: a flat universe dominated by dark energy, with a matter fraction consistent with what we observe, expanding at a rate that is slightly puzzling because of the Hubble tension, but broadly consistent with the cosmological constant model. The universe is big, the geometry is flat, the expansion is accelerating. The primary tool for probing the universe's true extent remains the CMB, and the primary measurement remains the geometry of its fluctuations. We have already discussed the flatness measurement. But there is another property of the CMB that constrains the size of the universe: the lowest, multipoles. The temperature fluctuations of the CMB can be decomposed mathematically into patterns of different angular scales, into spherical harmonics, which are the two-dimensional analogue of the sine waves you use to decompose a sound signal into its component frequencies. The quadrupole is the pattern with the largest angular sky, roughly 90-degree variations across the sky. The octupole is the next largest. In a universe that is infinite, or much larger than the observable portion, you would expect the quadrupole and octupole to have specific statistical properties, set by the quantum fluctuations of inflation. The WMPA and Planck measurements found something odd about the quadrupole and octupole. They are anomalously low, lower in amplitude than the best fit inflationary model predicts. They are not dramatically low, and the statistical significance is debated, but they are consistently low. One interpretation of this, one that has been proposed by cosmologists including Jean-Pierre Luminaire and collaborators, is that the universe is finite, with a size comparable to, or not much larger, than the observable universe. In a finite universe, the longest wavelength fluctuations are cut off by the size of space, just as the longest sound wave that fits in a room is determined by the room's size. If the universe were finite in all three dimensions, with a size of, say, a few times the observable universe's radius, the lowest CMB multipoles would be suppressed, roughly consistent with what is observed. In this model, the universe is not infinite, it is finite, and the shape of the CMB's low multipole spectrum is a direct imprint of that finiteness. The specific topology proposed by Luminet and colleagues is a dodecahedral space, a space with the topology of a dodecahedron, one of Plato's 5 regular solids, a shape with 12 pentagonal faces. In such a space, if you travel in a straight line far enough, you re-enter the same space from the opposite side. The universe wraps around. The size of the dodecahedral space that best fits the CMB low multipole anomaly is roughly comparable to the size of the observable universe, perhaps 2 to 3 times larger. This would make the entire universe still incomprehensibly large, containing trillions of times more galaxies than we can observe, but finite. Finite, and with a specific, non-trivial global topology that leaves an imprint in the pattern of the CMB. This is a testable prediction, and it has been tested. In a dodecahedral or any finite universe with the right topology, you would see the same distant galaxies or CMB patterns in multiple directions, circles, of matching temperature fluctuations on the CMB sky, at specific angular separations determined by the topology. Searches for these circles have been conducted in the WMA and Planck data. The results are ambiguous. Some analyses have found no statistically significant signal. Others have found hints. The sensitivity of the existing data is not quite sufficient to definitively confirm or rule out the dodecahedral topology. The next generation of CMB experiments, including future space missions that might improve on Planck's measurements, may have sufficient sensitivity to resolve this question, at least for universe sizes comparable to a few times the observable radius. This is science at its most ambitious, using a map of ancient light printed on the fabric of the sky to measure the shape and size of the cosmos itself. Not the shape of galaxies or clusters, but the shape of space, the topology of the universe. The answer to the question of whether the universe is finite or infinite, large or very large, simply connected or wrapped around on itself. The CMB is not just a relic, it is a diagnostic. It is the most distant surface we can observe, and its patterns encode information not just about the early universe, but about the global geometry of space, information that no local observation can provide. Information that requires looking at the whole sky at once and asking, does this pattern fit a finite space or an infinite one? The honest answer today is that we do not know, not with certainty. The measurements favour a universe that is at least as large as the observable universe, and likely much larger. The flatness measurement is consistent with infinite size, but cannot distinguish between a truly flat infinite universe and a nearly flat finite one, 100 times larger than the observable portion. Inflation strongly suggests a universe much larger than what we can see, and eternal inflation suggests a universe that is infinite, or might as well be. The CMB low multipole anomaly may hint at a finite universe, but the statistical significance is not compelling. The universe's true size, the answer to the question this video poses, is genuinely unknown. But unknown does not mean we have no idea. We have constraints. We have lower bounds. We know the universe is at least as large as the observable portion, 93 billion light-years in diameter. We know, from the flatness measurement, that if it has positive curvature, the curvature radius must be at least several hundred times the observable radius, making the minimum total size at least tens of thousands of billions of light-years. We know that if inflation occurred, and the evidence strongly suggests it did, the universe is almost certainly vastly larger than the observable portion, with vastly here meaning by factors of 10 squared or more in linear dimension. And we know that a truly flat, truly infinite universe is consistent with everything we have measured, and is in fact the prediction of the simplest version of the simplest inflationary model. What we do not know is the exact factor. The difference between 10 squared and infinity is in some sense infinite, but in another sense practically irrelevant. Whether the universe contains 10,181 galaxies, or infinitely many, the implications for how we think about our place in the cosmos are qualitatively the same. We are in a small corner of an unimaginably vast space. The observable universe, the portion we can see, measure, and interact with, is to the full universe as a single electron is to the Milky Way, or perhaps far smaller. The local patch of space within which all of human history has unfolded, all of human knowledge has been gathered, all of our instruments has observed, is a vanishingly small sample of what exists. This has implications that are worth sitting with. First, the universe beyond our horizon is not empty. It is filled with matter, with galaxies, with stars, with planets, and quite possibly with life, with beings who look up at their own patch of sky, who build their own telescopes, who derive their own physics, who wonder about the size of the universe from their own perspective. They have their own horizon. They cannot see us. We cannot see them. But they are there in the most probable interpretation of the physics. The cosmos is not a lonely place, because our observable portion is small and most of it is empty on the scales between galaxies. The cosmos is an overwhelmingly inhabited place if you count all of the unobservable regions that inflation implies. Whether those beings are like us, whether the physics in their region supports the same chemistry, the same kind of stars, the same range of possible organisms, depends on what exact values the fundamental constants take in their region, which in eternal inflation models can vary between bubble universes and which we cannot predict from our own physics alone. Second, the uniqueness of Earth is a question that has a different answer depending on which version of the universe you are talking about. In the observable universe, Earth might well be the only planet with life. We have no confirmed evidence of life elsewhere. In the full inflationary universe, Earth is not unique in any absolute sense. It is one of what must be an enormous number of Earth-like planets, scattered through a vastly larger space. Whether there are exact copies of Earth, down to the positions of every atom, depends on whether the universe is infinite. If it is, there must be. If it is merely very large but finite, there might still be close analogues, differing from Earth in ways too small for us to distinguish at this level of discussion. The answer to "Are we alone?" depends critically on which universe we are asking about, the observable slice or the full extent of space. Third, the question of why we find ourselves in a region of the universe hospitable to life, with the right value of the cosmological constant, the right density of matter, the right initial conditions for galaxy formation and stellar nucleosynthesis, takes on a different character in a universe much larger than the observable portion. In a single universe, the hospitable conditions seem to require explanation. Why are the constants the values they are, rather than some other values that would not permit life? In a much larger universe, and especially in an inflationary multiverse, where different regions can have different physical constants, the question has an anthropic answer. We find ourselves in a hospitable region because we could only exist in a hospitable region. Inhospitable regions have no observers. The fact that we observe hospitability is a selection effect, not a cosmic coincidence. This is called the anthropic principle, and it is deeply controversial, but it is not empty. It has the same logical structure as the observation that all organisms that exist are the products of a selection process that selected for survival. The survivors are not surprised to have survived. The observers are not surprised to be in an observable universe. These implications for uniqueness, for the prevalence of life, for the anthropic principle, for the meaning of physical constants, are where cosmology bleeds into philosophy in ways that are not merely rhetorical. They are genuine scientific and philosophical questions that the size of the universe bears on, directly and quantitatively. They are questions that arise unavoidably from taking the physics seriously. Consider the fine-tuning argument, which is often invoked in discussions of the multiverse, but deserves careful treatment here. The fundamental constants of nature, the mass of the electron, the strength of the electromagnetic force, the strength of the strong nuclear force, the value of the cosmological constant, take values that are, by any calculation we can make, extraordinarily hospitable to complexity. Change the cosmological constant by a factor of 2 in the direction of greater positive value, and the universe expands so rapidly that matter never collapses into galaxies. Change it in the direction of greater negative value, and the universe recollapses long before stars can form. But change the strong nuclear force by a few percent, and either hydrogen cannot fuse into helium in stars, or helium fuses so readily into carbon in the Big Bang that almost no hydrogen remains for stars to burn. The range of parameter values compatible with a universe capable of producing complexity is extraordinarily narrow compared to the full theoretical range. This is called the fine-tuning problem, and it is most acute for the cosmological constant. Quantum field theory calculations, without fine-tuning, predict a cosmological constant roughly 10 times larger than the observed value. That is not a typo. 1 followed by 120 zeros. The discrepancy between the theoretical expectation and the observed value is the largest unexplained numerical discrepancy in the history of physics, bar none. In a single universe with a single cosmological constant, this is simply a brute fact with no explanation. You accept that the cosmological constant happens to be this value, and you move on. In the level 2 inflationary multiverse, where different bubble universes can have different values of the cosmological constant, the fine-tuning has an anthropic resolution. If the cosmological constant varies between bubble universes over the full range, then the vast majority of bubbles are uninhabitable. Their cosmological constant is either too large for galaxy formation or negative enough for rapid recollapse. Those universes have no observers. The tiny fraction of bubbles with a life-permitting cosmological constant contain observers who, of course, measure a life-permitting value. This is the anthropic principle. We find ourselves in a hospitable bubble, not because it was specially arranged for us, but because we could not exist in an inhospitable one. The argument was made in quantitative detail by Steven Weinberg in 1987, who used it to predict that the cosmological constant should be small and positive, small enough to allow galaxy formation. Positive, because a negative value would cause recollapse. He made this prediction more than a decade before the discovery of the accelerating expansion in 1998. The observation confirmed the prediction. A cosmological constant that is small and positive, not zero, not negative, small and positive, exactly as the anthropic argument in the multiverse predicts. This is sometimes cited as the multiverse's only genuine predictive success, a prediction that preceded the observation. It is controversial. Computing the probability distribution of the cosmological constant across bubble universes requires a model of how the inflatant field settles into different minima in different regions, and we do not have a reliable model of this. The prediction is qualitative rather than quantitative in its precise value, but it is not nothing. It represents a case where the philosophical framework of the multiverse made contact with observation in a way that could have been falsified if the cosmological constant had turned out to be zero or negative. The anthropic argument in this form would have been undermined. It was not zero. It was not negative. It was small and positive. The next generation of experiments will sharpen all of these arguments. The Euclid satellite launched in 2023 by the European Space Agency is conducting a wide-field survey of billions of galaxies across 10 billion years of cosmic history, mapping the dark energy equation of state, whether dark energy is a true cosmological constant or something that varies in time, with a precision that will either confirm the simplest model or reveal new physics. The Vera Rubin Observatory in Chile, which began operations in 2024, is conducting the Legacy Survey of Space and Time, a 10-year photometric survey of the southern sky that will catalogue billions of galaxies, millions of supernovae, and hundreds of millions of variable stars, building the most comprehensive picture of large-scale structure ever assembled. The Nancy Grace Roman Space Telescope, planned for launch by NASA in the mid-2020s, will combine wide-field imaging with spectroscopy to map the three-dimensional distribution of galaxies with unprecedented depth. And CMB-S4, a next-generation ground-based CMB experiment involving telescopes at the South Pole and in Chile, that measure the CMB temperature and polarization with a sensitivity and angular resolution that will constrain the inflationary epoch with far greater precision than Planck, potentially detecting the imprint of primordial gravitational waves, ripples in space-time produced by inflation itself, which would be the most direct confirmation of the inflationary paradigm yet achieved. These experiments are not building monuments to what we already know. They are tools for discovering what we do not know. The Hubble tension may be resolved. The fine-tuning of the cosmological constant may find a physical explanation, or may remain anthropic. The topology of the universe, finite or infinite, simply connected or wrapped around, may be constrained by new CMB measurements. The evidence for or against eternal inflation may sharpen. The question of whether our universe is one of many or the only one may move closer to an answer, or may retreat further into unknowability. Science does not guarantee resolution. It guarantees progress. In the progress of the last century, from the static universe of the early 1900s to the accelerating dark energy-dominated inflationary universe of today has been the most dramatic expansion of the known in human history. The next century will be no less dramatic. It will begin with what we currently call the unknown, the universe beyond the horizon, the physics of the inflationary epoch, the nature of dark energy and dark matter, the topology of space, the question of whether the cosmos is one or many. Now let us return to where we began, to the night sky, to the 5,000 stars you can see with the naked eye, to the 2 trillion galaxies in the observable universe. That number, 2 trillion, was revised upward dramatically in 2016, when a team led by Christopher Kinselis at the University of Nottingham, we analysed deep field images from the Hubble Space Telescope and found that previous estimates had significantly undercounted the number of galaxies, particularly small, faint galaxies in the early universe. Their revised estimate suggested that the observable universe contains not 200 billion galaxies, as had been the standard figure for years, but more than 2 trillion, 10 times more. The revision was controversial at the time and has since been partially moderated by the James Webb Space Telescope's observations, which have refined our understanding of galaxy number counts in the early universe in ways that will take years to fully absorb. But the direction of the revision, upward, dramatically upward, is a useful reminder of how far estimates can be from reality when the instruments are not yet powerful enough to reveal the full picture. We thought we knew how many galaxies there were. We were wrong by a factor of 10. The universe surprised us. It will surprise us again. The James Webb Space Telescope, which began science operations in 2022 and is the most powerful space telescope ever built, has already revealed galaxies in the early universe at redshifts greater than 10, meaning they formed less than 500 million years after the Big Bang, that are more massive, more evolved, more structured than the models predicted. Large mature galaxies in the very early universe, when the universe should have been too young for them to have assembled. The discovery has prompted revisions to models of early galaxy formation, to estimates of the star formation rate in the early universe, and to the parameters of dark matter models that underlie galaxy formation simulations. The universe's early history is being rewritten. As each new instrument peers further and earlier, the picture changes. The cosmos is not a finished painting that we are slowly revealing corner by corner. It is something more dynamic than that, an object that surprises us at every new scale of precision, that revises our expectations every time we look more carefully. And this is perhaps the deepest lesson of the question we have been asking. Why might the universe be much bigger than we think? Not just bigger in linear dimension, bigger in complexity, bigger in structure, bigger in the density of its surprises. Every time in the history of science, when humans have assumed that what they can see represents the full extent of what exists, the assumption has been wrong. The ancient Greeks assumed the Earth was the center of the cosmos. It is a planet orbiting a star in the outer disk of a spiral galaxy. Medieval astronomers assumed the Milky Way was the entire universe. It is one galaxy among 2 trillion in the observable portion alone. Early 20th century cosmologists assumed the universe was static and eternal. It is expanding, evolving, and had a beginning 13.8 billion years ago. Now we assume that the observable universe is the universe. It is a horizon, not a war. A limit of vision, not a limit of existence. The pattern is consistent. Every expansion of our instruments and our methods has revealed a universe larger, more structured, more various than the one we thought we knew. Hubble's discovery that the Milky Way was not the whole universe but one galaxy among many took place in the 1920s, 100 years ago. A century of instruments, a century of mathematics, a century of patient observation, and we have gone from thinking the universe was the Milky Way to knowing it contains 2 trillion galaxies in the part we can see, and vastly more beyond. The next century of cosmology, with new space telescopes, new C&B experiments, new gravitational wave detectors, new computational tools for simulating and modelling the early universe, will almost certainly reveal a universe larger and stranger than the one we think we know today. The question is not whether the universe surprises us. It does, reliably, every time we look. The question is in what direction and by how much. The answer, based on the current best evidence, is much larger than we can see, probably by at least 10 squared in linear dimension, possibly by infinity. Certainly by amounts that make our observable universe a tiny and perhaps vanishingly small sample of the whole. The 2 trillion galaxies, the 100 billion stars per galaxy, the uncountable planets per star, the possible life on uncountable of those planets. All of this, the full richness of the observable universe, is a local fluctuation in a cosmos too large to fully comprehend and too fascinating to stop trying. You have been sitting here for the duration of this video in a specific location in space, on a planet, orbiting a star, in a galaxy, inside the observable universe, inside the full universe. Rather, that ends. The full universe is in all probability immeasurably larger than the slice you can observe. You are not at the centre of it. There is no centre. You are not near the edge. There is, in all probability, no edge. You are somewhere in a cosmos that has no privileged location, no special vantage point, no boundary that separates the universe from whatever lies outside. There is no outside. There is only more. This is not a sentence designed to make you feel small. Feeling small is the easy response, and it misses the point. The remarkable thing is not that the universe is large. The remarkable thing is that you are here, in this particular corner of it, with a nervous system capable of deducing that the rest of it exists, capable of measuring the curvature of space with satellites, of tracking the temperature of ancient light to 1 part in 100,000, of reconstructing the first fraction of a second of cosmic history from the patterns in that light, of inferring from those patterns the existence of a period of exponential expansion that lasted 10⁻³ seconds and stretched the universe by a factor of 10 squared 6 or more. The universe is not comprehensible in its full scale, but it is knowable, piece by piece, limit by limit, horizon by horizon. We have pushed our horizon back from 5,000 stars to 2 trillion galaxies in the last 5 centuries. We will push it back further still. The horizon is a limit of vision, not of existence. The universe does not end where our instruments cannot reach. It continues, in all probability, far beyond our light cone, beyond our causal future, beyond our most ambitious instruments, filled with structure and matter and the same laws of physics that we have measured here with such extraordinary care. The laws do not know they're at the edge of what we can see. The atoms out there obey the same equations as the atoms in your hand. The stars out there fuse hydrogen into helium by the same nuclear physics as our sun. The galaxies out there form the same structure of calm and the same bedroom race. It is all one universe, all one physics, all one vast and continuous fabric of space and time and matter, most of it beyond our reach, none of it beyond our curiosity. We are a small knot of matter in an enormous cosmos, and we have chosen to spend our brief existence trying to understand it. Not just the part we can see, all of it. Even the parts we cannot see, and may never see, and can only infer through the careful, patient, mathematical reasoning that is the finest instrument the human mind has ever produced. That is not small. That is the largest thing a mind can do.